So dynamically we have tectonic forces that are the engine. Then we have friction on faults, maybe pre-existing faults. So we have the accumulation of elastic energy and then a sudden release of kinetic, elastic, and part of frictional energy. So it's a complicated process. Can we decide, can we try to measure the energy released? The answer is yes, different processes. The oldest one maybe is to assign an intensity. And seismic intensity is a sort of the field of measures that are related to effects of earthquakes on the anthropic tissue, like buildings, like churches, like cities, like something that is man-made, and the effect. By the way, intensity is not a single number, because it's a set of numbers, maybe zero numbers. If an earthquake occurs in the desert, we have no numbers. And on the other side, if an earthquake affects a city, we have many numbers. So it's not a single measure, but it's the only one that we can use for historical earthquakes. What do we mean by historical earthquakes? Before instrumental seismology. And this means going back in the past. For example, in Italy, in the Mediterranean area, we can go back up to, with completeness, until 2000 years ago. Maybe in China, we have such a long catalog, but in other parts of the world, we have nothing, as you can imagine. But intensity is one way to try to give a...
You are recording?
No, yeah, I think I was pushing. It's blinking, so maybe, let's hope. So this is an example of a set of numbers with different degrees. In principle, intensity is a scale of integer numbers. There are many intensity scales. We will not enter into the details. It's not an easy process to assign a number, also because it depends on the vulnerability of a building. So you can say, okay, that building has been partly destroyed, but was it vulnerable? Was it really well built? So modern magnitude scales try to overcome this and decide to assign different numbers to different kind of buildings, using a sort of a taxonomy for buildings, so reinforced concrete, steel, something like that. But in principle, it's a set of numbers. And we don't have one number for one earthquake, we may have many, we may have none. As you can imagine, it's not easy to assign these numbers for historical earthquakes. Like, I don't know, the most famous that affected this area occurred in 1511, but you can imagine the city of Trieste, for example, was very tiny at that time. So we have uncertainties. So in some way, it's a weak parameter, but it's the only parameter that we can use for historical earthquakes. So it's very important, also for hazard. By the way, this is one example. So we have a sort of what is called macroseismic field. In principle, it's a field with different numbers. Of course, we have to take care that it depends on the vulnerability of the buildings. We may have some hotspots associated to some local amplification, so geology is important. Think about, well, maybe in the last lecture, I will show to you again the case of Mexico City destroyed by a Michoacan earthquake. So you can imagine that the patch in that case, the epicenter was on the coast, but the maximum affected area was 300 kilometers away. So that's not easy. You could say, oh, there is an earthquake in Mexico City. No. So, by the way, it's one way to measure. It's the only way that we have for historical earthquakes. The only one. Some other things that may puzzle seismologists is, for example, let's consider the 1906 San Francisco earthquake, very famous, it affected California. We have seen the recording of this earthquake in Japan. If you remember, it was one of the first seismic recordings in the world. Okay, on the other side, in a totally different part of US, around Missouri, we have a famous, maybe one, maybe a two, maybe a set of earthquakes that occurred in 1811. It's very uncertain, but you see that the numbers can be the same. And we see that the scales are starting from 1, usually 5 and 6. They have different names. For example, in the US they use modified Mercalli. Mercalli is an Italian surname because he was one of the first to establish the sort of a European scale. Then here it has been used with Kankani and Seeberg. It's called MCS. Japan has another scale that is called Shindo scale that is using 7 degrees. So it's a sort of a mess, but okay, there are different scales. The idea is the same. Try to give a number according to the damage. So usually from 10 or 12, that is the maximum, until, let's say, 5, we can feel it. Less than 5 usually is a sort of an instrumental earthquake. That's one way. Again, it's not easy. For example, here we have two totally different macroseismic fields, as you can see. Look at the Missouri one. It's spreading on a wide area. Well, that's funny because maybe on Monday we will understand why. Because we can say, oh, the Q quality factor of that region is much higher, so waves can propagate much more efficiently here than here. So it's another factor that can decide the macroseismic field. And this is also a puzzle for seismic hazard assessment. Should we say that Missouri is at the same level of hazard as California? There is not an answer to that question. This is an example of a table that I was putting here. Do you have in your notes this one?
Yeah.
Okay. Still don't have the strong bushy one. Modified Mercalli, Rossi 4L. This is the Japanese Meteorological Agency scale. Mercalli, Kankani, Seeberg, and this is I don't remember. These are 3 different surnames, but usually it was it's written here. And this was used and it is still used nowadays in Eastern Europe. So you see different patches. And that's the idea. Now, can we do something better? Maybe trying to estimate the energy of an earthquake, because this is the damage. So maybe can think about, for example, a magnitude 6 occurring in central Italy. That was the case. It was affecting and destroying many buildings here, because we have ancient middle-aged cities with very large vulnerability. If you imagine to take the same earthquake and you put it in Japan, probably nothing is going to occur. So intensity could be 6 in Japan and we have 11 here. So you see, it's not a direct measure of energy. It's the measure of an effect of some storm motion shaking. Can we do something better? Yep. After the development of instrumental seismology, as I told you, Charles Richter, for example, was trying to answer the question: can I give some number to the news so that the people can read something and understand something that is related to the energy of an earthquake? So let's imagine to be in California, we have many earthquakes of what now we can say magnitude 6, up to 7 maybe. And maybe someone was shaking for an earthquake, maybe stronger but occurring at a more far distance, like in Mexico. So that was an attempt to estimate the energy of an earthquake. And that's intensity, that's magnitude. I was putting here a couple of plots of the idea that was behind the procedure that Charles Richter decided. The paper on which the definition is based is dated back to 1935, so not that long time ago. And he was plotting for different earthquakes the amplitude of the motion, because he could use a seismic network in those days. It was based on Wood-Anderson seismometers. Now we know a Wood-Anderson has a response, a transfer function that is not flat. I was asking Stefano about the definition of a low gain. He was agreeing with me. Stefano Prole, that is going to teach me next. He was agreeing with me that low gain maybe means small g in that equation. so something that is not amplifying too much the motion. Okay. Sorry for this parenthesis. So we have an instrument. He was using an instrument with a specific response. He was aware of that, and that's why later he agreed to call this magnitude local magnitude, and that's why usually it's used here with the letter L. Okay, but it's the original definition by Richter. And the idea was to plot amplitudes versus distances. And he was noticing that there was this trend, okay, decaying, we know, on average, geometrical spreading, inelasticity, Monday, maybe some bumps due to source effects, but at far distance. Usually we have this behavior here. But the really point of Charles Richter was to use logarithms. Because if you don't use logarithms, these dots will be messy. But with logarithms, everything was running smoothly here. And so we decided to put different numbers to these different earthquakes. How? Using this. That's a very simple definition of something that is based on the logarithm of an amplitude, but referred to a sort of standard amplitude. And he was using this A0 based on his instruments, his conditions, whatever, so California, and it was the amplitude of 1 micrometer recorded at 100 kilometers from an earthquake. That amplitude is the reference one. So magnitude 0 means, okay, I'm recording exactly that amplitude because that's 1, 0. Okay?
Yeah, a little bit distinct log, yeah?
Yes. But if I'm able to record something lower than amplitude, okay, that it will be a negative magnitude. But it was so smart to use that reference amplitude as a sort of a threshold of noise for him. So all the magnitudes were large. But nowadays we can record events with -3, for example. Okay, that's the idea.
What magnitude is -3? What does that mean?
Look at this definition.
Does it mean?
What about the logarithms? Can they be negative?
Yes.
Yes, whenever the argument here is less than 1.
Yes. So
At that time, he couldn't measure because the sensitivity of these instruments was not allowing to record something larger than A0. He was marked. But nowadays, the sensitivity of a modern seismometer, remember the dynamic range that we have been mentioning on the previous lecture. Now we can record much smaller amplitudes. And this means that they could be -3.
that means it will not be deadly.
Pardon?
It means it will not be.
If you're not sitting on that one, no. Just a small shaking.
Okay.
So it's called instrumental seismicity. Something that we cannot feel. Okay. I added this slide. I don't know if you have it. Is this in the notes? Okay, good. Because I added it during the last year. And because I found this interview with Charles Richter in the news, as you see, you can find it here, the whole interview. And actually, he confessed that the idea to use logarithms was coming from Benno Gutenberg's suggestions. He was working in his observatory at the time. He was one of the most famous seismologists at the time. And he was a sort of a naive astronomer. So the idea to use logarithms is in astronomy when you want to measure the light from a star. And logarithm occurs whenever you want to squeeze different scales, because it's putting powers to products. So it's easier, like decibels, mountain. So that's the idea to use logarithm. That's the original plot. You see, without the logarithms, it would be a mess. With logarithms, these trends have been used by Charles Richter to define magnitude. Just to visualize it, if you want, let's consider, for example, 2 earthquakes, and you see they are very different. Okay, you see the recordings? They could be very different because they could come from different distances for different events. So it's not easy. Well, the procedure is, for example, to use the arrival of a P wave, of an S wave, if you remember, I hope, you performed an exercise in the wave physics course, and you had been using the difference in arrival time between Vp and Vs to measure a sort of an average velocity. Okay.
That's homework.
Right. So if you know the structure of the Earth, with this information you can trace the distance. And once you have the distance here, you see S2P in seconds, that's the distance. You use this scale here, and if you read here, and if you take this, and if you take 100, and you put it here, you will get a magnitude 3. I'll leave to you the exercise to answer why. Now let's imagine to take 100, okay? Distance 100. You join the 100 with -1, that is the bottom of the scale, this case here, okay? And you use this scale to read magnitude. That was the sort of instrumental vision. So you have a scale of distance, a scale that is fitted just to its definition. Remember, an earthquake at 100 kilometers that is given an amplitude of 1 micrometer. Okay? Micrometer is 10 to the minus?
3. Minus 6.
Okay. Well, okay. So here, if you use 0.1 millimeters, you got a magnitude 3. It's up to you. By the way, with another distance, and you join the amplitude that you're reading here, okay, you got a measure. And here you have another measure. Same distance, but larger, as you can see, okay, you're getting a larger number. That's magnitude. It's an instrumental definition, based on a specific instrument. Problem. Look at these two signals here. They're very different. They're definitely expressing two different earthquakes. But if you use a specific instrument, you're magnifying a specific part of the ground motion because it has a response. I hope you do remember. Let me open the previous lecture. And if you remember somewhere, there is. Okay, let's see, there is Wood Anderson. Okay. You see this one? Okay, so it has a peak. So different parts of the ground motion are not amplified as those ones. That's a problem. He was knowing this. And so later there was an attempt to change this. Because look at the difference between these two signals. The top signal is recorded on a modern broadband. Now we know it's flat, okay?
Yeah.
But look at this. This is the same signal, but as recorded by Wood Anderson, magnified. Wow, they are very different. So if you take the maximum amplitude, you will get different numbers. So the problem is, okay, if I'm going to use a different instrument, I will get a different number. So it's not a direct measure of energy. It's connected to
Instrument.
the numbers that Richter was recording in California and to an instrument.
So
Local. That's why now we have L. So if you read somewhere ML, you know that it is the Richter based on this definition. And up to now we can use this definition and try maybe to couple magnitude with intensity. Remember that this process is not unique. There is an attempt, maybe if you're recording something like 8 or higher in intensity, maybe you can associate it to an earthquake that on average has a magnitude larger than 7, but that's not always the case. Remember that these numbers here, so you have also now an example of now intensity degree is given, you see here, well-built wooden structure destroyed. So you have to go on the field and to decide, is that destroyed? You could say yes, no, or maybe no data, maybe the same earthquake, different buildings, different earthquake. It's a mess. So this is just an attempt to couple intensity with magnitude, but it's not unique, okay? So that's the summary up to now, to this slide here. Now we have intensity, we have an instrumental way to measure energy, but we have also some problems. Can we overcome these problems? There was an attempt, for example, to use different magnitude scales, and using different parts of a wave field. Because we know, okay, we have body waves, do you remember? We have surface waves, do you remember? Different amplitudes. And they are, how to say, they are carrying different information also in terms of frequency, of period. So the idea in the 70s, in the 50s, between the 50s and the 70s, was to use different parts of sections of a wave field. For example, high frequency body waves. And now you get a small b here, body. And by a sort of a definition, it's using the information carried at 1 second. So you take the logarithm of an amplitude of the ground motion with a period of t equal 1 second. Plus some correction, because of course you need to equalize different earthquakes at different distances. You have to put them together if you want to compare them. So you have some functions here that are correcting for depth or for some regional propagation characteristics like high Q regions. So you're trying to put them at the same level and to use the logarithm of an amplitude at a specific period.
So log E by T. So E is amplitude, yeah?
Yep,
And T is time period.
right. So you're not happy with that. I'm not happy with that.
Yeah, I know.
Mathematicians are not happy with this, but seismology do not care. They do this. Yeah, it's funny. But there is so bad news because we are using dirty numbers for a logarithm. That's the definition. Good news, A over T, what is?
It's velocity.
Amplitude, it sounds like velocity. And velocity squared sounds like
Sounds like
Energy, force.
kinetic energy.
Energy.
That's why also A over T is there. You'll see in one later slide. Because you're trying to measure something related to energy.
mhm.
So for physicists and not mathematicians, that's a good definition. For mathematicians, it's not. I know. That's it. For surface waves, and you see here the label is S and capital M, that means surface waves, and you're taking the vertical component of a Rayleigh motion at 20 seconds. Why vertical? Usually. You can use also the horizontal, but it's more tricky. Think about it. Can you separate Rayleigh from love? You can say yes.
Yes.
One is plus V, the other is SH.
SH, yes.
Easy. Not easy. Because if you compute synthetic seismograms, like what I'm doing every day, that's easy. I have a receiver, a source, that's Rayleigh, radial component and vertical, right? And that's love. SH, right? Very easy. But in practice, you're recording this on a north-south seismometer. So you have two components of horizontal motion. How to separate them in love and Rayleigh? You have to know the source, the position of the source. If you know, okay, you take this angle, that's Rayleigh, that's love. But you have uncertainty here in real life. So your decomposition in the horizontal components, sometimes it's not easy. But vertical will be Rayleigh. That's why. As a standard vertical component of a motion is used, because that's Rayleigh. Okay? So that's it. That's the end of the lecture. We're done. Goodbye. That's nice. It's physical, it's instrumental, but using different parts of a signal, as we know. So for example, you see these tiny amplitudes, definitely they are smaller than these ones. Why?
Because they use the different
What was
instrument.
decrease faster than surface wave?
Why?
Because of surface wave is 1 over square root of distance, and body waves is 1 over
Because
distance.
body waves are spherical waves, 1 over r, while Rayleigh waves and love waves, they are
1 over square root.
space waves, so, okay. So, but we know, so we can use different amplitudes at different periods, trying to get the same number. Do we? No. No. For example, let's imagine that we want to record an explosion. Not nice, but in the 60s, that was the problem. An explosion is much richer of body waves, of P waves, compressions and rarefactions. And S waves, on average, they are excited less by an explosion than an earthquake. That was one of the ways to separate signals from explosions and from tectonic earthquakes. Because MB should be large, MS small. Okay? And that was one of the reasons to use MS and MB. And still nowadays, MB is used for this reason. Okay, so that's natural, but actually we have another problem. Because for earthquakes now, let's forget about explosion, let's consider earthquakes, for example. Well, we would like to have the same number. Well, we are measuring energy. So ML, MB, MS, they should give the same information. They do not. They don't do this. That's one example. So MS is pretty much the same, but MB is not. And we have other cases in which these numbers, they don't agree. Why? What's wrong here? Because actually, in the field, they realized with the, how to say, really the development of the worldwide standard networks in the West and the East of Europe, for example, there were a lot of cases in which MB was different and smaller than MS for earthquakes. Actually, they noticed that MB couldn't overcome a given number, like this one. They can't. No earthquake was giving numbers larger than this, while MS was growing. But also MS at a given point was not giving numbers larger than 8.2. So that's called saturation. So we have a problem here. Let me forget about this. Okay. And let's go here. Now, let's give a look to these two signals. Look, I was just keeping word in simple slides. Do you have questions?
No.
Just a set of iron balance here. So as a rule, MB has to be measured in the first part. It's related to P waves. Okay, you take this, and they're giving the same number, but look at the other part of the signal. So they're giving the same MB and saturated because we do not overcome. But here, the rest of the wave train, the later part, is much larger in these two cases. So these two signals are evidently coming from different earthquakes, and this is larger than this. Good. So MS is better than MB. It's not saturating, right? Well, it was saturating as well. And that's a simple but quite clear evidence of something that is reaching the roof. Is that physical? Or maybe there is something in the definition of the amps, of the magnitude, that is, something is puzzling there. Well, you know the answer, because I told you a couple of lectures ago. That's related to the source spectrum. And it's related to the fact that both of the magnitudes, of the instrumental magnitudes, MB and MS, they are taken at specific periods. 1 second, 20 seconds. So 20 is longer than 1, but not enough to measure earthquakes with a magnitude larger than 8. Now, That's the story. And you know, because we discovered that the source spectrum, if you take the logarithm of something here, maybe the logarithm of the amplitude. Oh, yeah, it's magnitude, right? It's the logarithm of an amplitude. And here you take log of f. We discovered from the Haskell model a couple of lectures ago that it should go like that, and like that. Now, what is the roof here? Well, the roof is from this one and longer periods or shorter frequencies. But if we measure it here, that's a problem. Please do remember that this quantity here is related to M0 of an earthquake. And that's the key parameter to be used. One way to use it is to go to some periods. But in principle, you should use these ones. Because this is getting larger and larger, but these are not. Just due to the fact that the source spectrum is not flat. It's flat, but up to a frequency. Then it's falling. That's the reason, that's why instrumental magnitudes at 1 second and later at 20 seconds, they are saturated. So what do you suggest? Don't worry, because the problem was solved by Kanamori and Anderson, 1975, and 2 years later by Kanamori. But you can try to solve the problem. How to measure something that is not a saturating pair? Let's go to zero frequency. That part will never saturate, right? Oh, easy to say, not so easy to do it in practice. Because infinite period, do you have something at infinite period? I told you, you can use the modes of the Earth. That's very long periods. You can use the near field. I told you, because you have a static displacement there. But it's not easy because you need a GPS near the fault. So in practice, after the definition of what we are going to call MW, that is moment magnitude, that was using that spectrum and in principle to overcome the problem of saturation, in practice it was related to long period measurements that are the surface waves at 100 seconds. And that's fine for most of the earthquakes, but if you're considering a mega earthquake, magnitude 9 and larger, that's a problem, because that period is not long enough. That's why I will assign to you today a homework, but it's a very nice one. Because I will ask, let's see if I put it on the, if the PDF is here. It should, if not I apologize. Okay. It should be this one. Let me see. What's this? Oh, they removed. It was free 1 year ago. Maybe you can use it. Let's see if I can grab it. Because usually it was on the... Let me check. Let's see if this is free. Okay, the same authors, but the Toku event, and same pictures and same principles. But let me check for stay. Stein is the same set Stein of your textbook. Let's see if I can steal it from the web. No. I'm not able to grab it. Well, that's your homework.
The paper?
Yep.
To read the paper?
Yes, it's a very tiny
Thank Thank
It's
you.
a 3 pages paper, and with pretty much no formulas, except one maybe. Why it's not? It was freely available in the Stein. Well, it's on Nature. We should have access to Nature. Oh God, please give me some money.
Yeah, I'll take it back.
Wow, no, but usually Nature should be accessed by the ICTP library. We have a subscription. At the university we haven't. Let me try with the... Okay, that's your homework.
We can download it from the medical library website.
Yeah, I think you should try later. By the way, okay, they have been studying the Sumatra event. It was a very important event. It was a tragic but important event because there was a tsunami warning. At that time, there was no tsunami warning center in the Indian Ocean, but there was a very effective one in the Pacific Ocean. When they recorded the surface waves from that event, in let's say 10 minutes, magnitude was estimated using surface waves, and it was released as 8.8 magnitude. So warning started. But it was not that, how to say, wow, that's a real warning. Because actually, the Sumatra event was so large that if you give a look to surface waves, it was an 8.8. But later, they had been studying the normal modes of the Earth and tsunami, that is a long period signal, and they assessed that the magnitude was 9.2, and that's why the tsunami was so large. 8.8 and 9.2, you could say, well, what's the difference? Remember that magnitudes are logarithmic, so it's a huge difference. And they had been using the modes of the Earth, yes, the same modes that you studied in the wave physics, as O2, for example, to assess at longer periods the magnitude. Remember, SO2 is 54 minutes, so it's 1,000 of seconds. That's the idea. That's the idea that was developed in this beautiful paper. There are many versions, and there was a simple one. Let's see if I can access. No. Okay. It's your. If you go to this website, to the Moodle. Okay, you can find this, but it's about Toku, and it was here. You can try to trace. It's your homework. Okay. Now let's try to go towards this part here. Let me skip it and let me go directly to the point. That's the problem. So now if you go back to the beautiful Haskell model that we discussed 2 lectures ago, so with the finite fault, you remember, rupture was starting from one side, propagating. We discovered flat 1 over omega squared, right? And the first part is proportional to m0. Okay? m0 we know, it's mu times A times the average slip. Okay, so to sum up, this is what happens if you take the logarithm of the frequency. Here you take the logarithm, that's a prequel. Let's imagine that we have logarithm of the amplitude here, and if we use MB, and it is defined at 1 second, you see that sooner or later you reach the roof. You cannot get larger numbers than this, and this corresponds to 6 point something as a magnitude. You cannot go over. End of the story. If you use MS, now you're going to longer periods. So it's 20. So you can reach higher grounds, but not that much. So you cannot get a number larger than 8 point something. At that time, there was a seminal work by Kanamori and Anderson, and this is what we are going to study now, just in 3 slides. It's a sort of a summary of the paper. And they had been using the theory that we developed 1 lecture ago, 2 lectures ago, using what we can call scaling laws for earthquakes, and they tried to use the data that was available at the time, 1975, in the early 70s, for the large earthquakes that they studied. So they used theory, very simple one actually, and they tried to use the data available and to divide them in quadrants. We will see what's going to occur there. By the way, to sum up, the idea is knowing the source spectrum to go to longer periods to avoid saturation. How much longer? Oh well, let's imagine to go to 0 and we can read m0. Given m0, let's take the logarithm of that value. That's the idea of a moment magnitude. So the end of the story is, let's use mw. Why w? Kanamori said it was the first available letter after BC, because there are many other magnitudes like duration magnitude, so he used w. But you can remember it thinking about work. And moment is a work, because it's a force times a displacement. So units are those of work. That's the idea. So the solution, and it is giving the magnitude that it is used nowadays, is to use moment. Let's give a look. Okay, let's recap for a moment. Okay. Let's try to follow by easy steps what Kanamori and Anderson did. First, they had been looking at models of earthquakes. And they had been thinking, okay, what is an earthquake? Well, it's something, as we know since the first lecture, that is accumulating stress, sleep is occurring, and stress is released. Okay, let's imagine to be seated on one point of the fault to measure stress. It's increasing before the rupture. Rupture is occurring, it's falling down, and then we have a new level. Okay? That quantity is very important to describe the source, is called stress drop. So the stress before, the stress after the earthquake. That quantity will be proportional to the energy. That's easy. Now, stress is usually related to strain. Can we imagine a strain drop? Well, we have the 2 sides, the 2 blocks on the fault, before the earthquake, after the earthquake. So we can assign a sort of a strain drop as the slip occurred during the earthquake over, remember strain has no units, okay? It's a pure number. So the slip over the initial length of the fault. Stress drop, strain drop, okay? Easy. And that's the initial idea. So we have a stress drop, we have a strain drop, and they have to be related by. Yes, and in very simple model for, let's say, homogeneous media and the shear dislocation, there is mu there. Okay, elastic constant. And then a constant that depends on the geometry of the fault. That's very easy. Stress, strain. Okay? Good. Then they had been thinking, okay, let's try to use some scaling laws. What does it mean? Let's try to put earthquakes together. For example, let's imagine that the width of a fault and the length of a fault are scaling. So larger earthquakes can occur, but this ratio is constant. It's a sort of the aspect ratio. Okay? Pardon?
Material dependent quantity.
Not this one. That's width and length. Actually, width will saturate, because remember that earthquakes can occur just in brittle materials, so in the lithosphere. So sooner or later, you're going to reach the bottom of the lithosphere. So you can just go longer. But in principle, larger means you're increasing the width, you're increasing the length together with a given aspect ratio. Another assumption for the scaling laws, to try to put simple things there. The ratio between the slip of the fault and the length of the fault is a constant. Good. Using these definitions, moment can be defined using those parameters. It's mu times the area times the slip, right? So you can rearrange it using this. And for example, you can rearrange them using the stress drop and, for example, the cube of the length. They were looking for powers, okay? Or, for example, stress drop and its proportional to the area. Different ways to rearrange it. Looking for simple things. Then they used the last one, that was a kinematic property. Now, let's take the ratio between the rise time and the rupture time. These are the two kinematic parameters that we have defined and used in the past. The ratio is constant. They call it a dynamic aspect ratio. Actually, it's a kinematic ratio. And they have been looking with this same simple definition to test, okay, is there really a dependence with these powers of these values here between M0, area, length, and stuff like that? So they have been looking at data. And you will see, okay, just to relax you, this slide is coming from your textbook. So the same argument is treated on not only in my messy way, but also in the textbook, if you want to relax. Why I like this? Because here it's exactly what we have been defining here. There is a ratio between rupture time. Oh, by the way, I noticed that in the previous -2 lecture, you had been pointing at right thing here because I was using a small r in TR. If you remember, you had been asking something related to that. In some of these slides here there was a small error. But actually, just to use the same definition, rupture time, I corrected them with capital R. I'm simply saying that in some of the previous slides here, rupture time that was length over rupture velocity, I used small r in some slides, no, so I replaced it with capital R. Do you remember that you had been asking?
Yes.
Okay, so I noticed that there was a mistake or something, just a typo, okay?
Okay.
But this is TR, as you remember. And it depends on the activity. Okay, good, let's go back. And this is just to show to you how, on average, rupture time and rise time, they are very different. And rupture time for large earthquakes is much longer than rise time. Okay? As we know, rupture time is the time necessary for the rupture to start and to stop. Good. Here it is an example of their plots. So they have been using the data available until 1970, let's say 4. Some large earthquakes occurred, and they tried to draw very simple plots just to check these scaling laws. At that time, the best magnitude available was ms. Okay? So, logarithm of an amplitude at 20 seconds. Okay? Good. An example of their plots. You see that's the paper that is used here. What do we have here? Logarithm of an amplitude. Why? Because it's the quantity that is related to magnitude. And here you see the logarithm of m0. It was one of the first attempts to put the things together. Here they have been using, for example, the hypothesis of constant stress drop. Actually, if you draw these plots here, all the earthquakes occurring in the normal tectonic Earth are between 10 and 100 stress drop. But remember, it's bar, so it's quite a large quantity. It's not pascals, okay? Good, you see this order here. They are very well behaved. And this is one of the first time in which there is a relation between the logarithm of the moment and something with a very simple number pair. Please do remember that 3 over 2 because it will appear later. Now, for the final plot that we have to look, and it is the most important one, let's go back to what we studied 2 lectures ago. I know that you love it, but this is the expression of what? Of a spectrum of a displacement, averaged for radiation pattern, equalized for distance, and if you remember, it's the convolution of 2 boxcars, and in the Fourier domain, it's the product of 2 sinc functions. One is related to tau, the other is related to rupture time, right? Do we agree on this? Good. And we said, good to know. Now, let's take the brutal approximation of what? Well, okay, a boxcar, we know it's something like that, bumping up and down, but let's take it like that. So flat and then falling down. If you multiply 2 of them, one longer, what does it mean? Maybe shorter here, there will be a range in which both are 1. Okay? Which one? Well, we have to consider frequencies. If this is larger, this is 2 over TR, this is 2 over tau. Okay, here they are flat, right? Then here, 1 over, here, 1 over square. Good. And this is what we use to draw the source spectrum. And so here, I just replotted that expression. Okay? So we have different regimes. But wait a second. Now let's give a look to these expressions from a different point of view. Here we know we have M0, M0, M0 times here. With those scaling laws, we have different regimes scaling with length. And now we can use a reference period. Which one? 20 seconds. So let's compare these quadrants here using 20 seconds as a reference period. Why 20? Because it is the period at which MS is defined. So they said, okay, let's take that period, let's compute omega from that period, so 2 pi over 20, that's omega, 0. And let's give a look. What about 2 over TR and 2 over tau respect to this period? Let's see. Now, let's take 20 seconds, let's take this, but now as MS logarithm of A at 20. Now we have different regimes. According if, okay, is the rise time, so here T, capital T is 20, okay? Is the rise time less than 20 over pi? On average, yes, because it's very short. Okay, is rupture time less than 20 over pi? No, for larger earthquakes, it's not. So which one would you choose between all of them for large earthquakes? Usually, rupture time, not the last one because rise time is not very long, but this one is okay. So that's the one that we can use and to check about the available earthquakes. Now, if that's true, look here. We have, using those scaling relationships, what we can add here is that the logarithm of A over 20 is related to 2 over 3 log of M0. That's the key step, because Kanamori 2 years later said, okay, let's take it vice versa. Let's take this as a definition of a magnitude. Okay? By the way, that's the plot that they have been using and looking at. So now you understand that here you have rupture time, that's rise time, and these 2 lines here are referred to 20 seconds. You see that all the events or the most important one, except some outliers, they are here. And that's the key point, you see? So they had been checking, but since they knew that there was saturation with the mass, they said, okay, let's use the theory here and let's take it vice versa. Let's use this as the definition of a magnitude. And Kanamori called it moment magnitude. So the final step is the following, and that's the recap and maybe the most important slide for today. So a set of empirical studies, Kanamori-Anderson, you've seen the plot. Gutenberg and Richter, some years before, they tried to measure the energy, and they found this empirical relation. Again, there was energy related to magnitude. You have seen before something like that. Again, if you take velocity, this is what you have been asking before. Let's take an harmonic wave, for example. Okay, velocity will depend on a over t, as you can see. So the logarithm of a over t is related to energy. So all the indication about energy was pointing to magnitude. Haskell model was pointing to magnitude, but vice versa, and this is what they did. So they said, okay, let's take m0, let's take the logarithm, let's multiply by 2 over 3, why? It's but 3 over 2, but it's coming from the Haskell model. And then let's do one final step. Let's choose a number here so that for magnitude 8, this scale and the mass are giving the same number. Okay? The number that you're getting is this. Pay attention because this is the number if you use Newton times meter for moment. That's International System Unit. But in many cases you can find dyne centimeter, so the CGS unit. In that case, the number that you find is this one. And that's it. So what do we have here? Well, we have different magnitudes, as you can imagine. Which one we should use? Well, for early instrumental seismology, the most used was ML. But after the 50s until the 70s, the more used were MB and MS, but saturation. So let's use the new one, and let's use the moment, taking the logarithm, multiplying by 2 over 3, and the number so that this line here is touching MS at 8. And it's giving to you this number here. Now this new scale, in principle, does not saturate. Because if you measure the moment, now you get a number that in principle will not stop. Only physics will stop it. Because up to now, we never noticed an earthquake larger than 9.5. And it is the Chilean event. So here you see sort of the summary of the large events, of some large events in the past. Now if you give a look to this, you see that MB is never getting larger than 6.2. Here, MS, also for very large earthquakes, is not getting larger than 8.3, 8.4. But if you take MW, now it's not going to saturate. So you measure M0, take the logarithm, 2 over 3, and that's coming from the Haskell model, it's 1.5, okay, and let's go. It's beautiful, isn't it? And also this is beautiful, because now, thanks to this slide produced by Seth Stein, we can see how different are earthquakes with just maybe small number differences in magnitude. Remember, it's a logarithm. So for example, what about this? Wow, it's tiny, isn't it? This is tiny. Let's look at this. That's the Sumatra after their assessment. It's huge, okay? But question, how to measure M0. Oh, you could say, come on, it's easy.
mu times k times average.
How it is defined?
Mu times k times.
It's easy. How to do it?
Go to the pure.
You can go with the meter on a fault. In practice, it's not easy. You can estimate an average mu for an area, phi. But how to measure A? Most of the events are on blind faults. So you have to use other information, like for example, distribution of aftershocks. You can use INSAR, maybe nowadays, but not for all the earthquakes. How to measure the slip? You cannot go on the fault. In some cases, yes, you can measure it. You can use Seismology, you can make trenches and measure it, but you cannot do it on a routine way. So how to do that? Using the best available information, waveforms. The longest ones, the longest period ones, surface waves, 100 seconds, 200 seconds. But for a magnitude 9, that's not enough because we're reaching the floor again, 8.8. So we should go longer periods. Modes of the Earth, 3 modes of the Earth, static displacement, but it's not easy, or tsunamis. Because tsunamis, we will see in the last lecture, they are long period gravity waves. Their period is about 1,000 seconds. Okay? So, in principle, the solution is given. But in practice, it's not always trivial. Because the practical estimation of M0, it's not, in many cases, trivial.
Sorry, can you go back and one more? And maybe here? No, sorry. There was a table somewhere. Oh, it is. It seems like for the surface wave magnitude, like for smaller earthquakes, is overestimating than the moment magnitude. So it's overestimating.
Let me tell you one thing. When you read a magnitude value, wait. What I'm trying to say to you, there are uncertainties. My opinion is never trust the last digit of magnitude because usually it's estimated, but it is on average plus minus 0.2. So maybe you are pointing to beautiful numbers here. Let me give you a look. Which one? This one?
All 3 first, 4 first, actually.
So you're saying, well, 6.6, 6.7.
Sorry?
You're comparing MS with MW.
Yes.
Okay. This actually 0.1, 0.1 difference. This is 0.2, but wait a second.
And 0.4.
But how you measure these numbers? The message to take home from this table is these two and these ones. Now, please, let's imagine that every digit that is reported here has uncertainty. So that's why I don't believe to the last digit here. On average, also on modern magnitudes, there is a 0.2 error in them. Are you getting my point?
Yes.
So these two numbers, in some way, they are the same.
What about
Can you imagine how to measure this one? There it is given, okay? Because you have an average dislocation, 1.4. Do you trust it? Okay? So it will be 1 plus minus 1, or 2 plus minus 1. So here you have an uncertainty every time of 0.2.
What
So-
about the San Francisco one?
Well, look at the date.
Farina.
Okay, I think that the available recordings there, they were on, how to say, they were on paper. So after digitization and then looking at the amplitude at t equal 20 seconds, it's not so easy. So I wouldn't trust too much this number here. So you could ask, why you're putting those numbers? I was grabbing this table. My message was related to these two, 9.1, 9.5. And the most impressive one is not this, but it's the one related to this one, because MS was 8.8, plus minus, minus 0.2. But actually it was 9.3 at least. But please, my message for you to take home, never trust to the last digit of magnitude. For example, let's give a look to a routine output of a bulletin. You have one in the first lecture, I hope. Because when I was using the Toku event, oh, now we can read that one. Okay, a long time ago, at the beginning of this course, here it is. Now, these are two solutions given by two global centers. This one is USGS and this is CMT. They're both located in the US, but we are using worldwide recordings, and in, let's say, 10 minutes, we are releasing this bulletin. Okay? 10 minutes, the 3 modes of the Earth are not there yet. Okay? So they are using surface waves arriving at different locations, and of course, these estimates are updated because you need some time for waves to reach the other part of the world. Okay. By the way, now we can read it because now we know all the parameters here. The first, 9.1, that was Toku. They knew after Sumatra to use the longest period as possible. Okay? Now, SMT. Let's give a look to this. Origin time, moment tensor. Now you know what is a moment tensor, right? Mij. Mij is one way to express the double couple, right? Okay. Skip 10 to the 29th power d in a centimeter. Now you know why it's a moment, okay? Then you have the 6 components. Why 6? It's symmetry. Good. Other possibility, T and P, the axis. You remember? Null axis, traction, pressure for the source. Otherwise, best double couple, strike, deep, slip. Why there are 2?
Two strike?
Yeah, there are 2. Why 2?
Because
The fold and the auxiliary one.
yeah.
And so you can read this or the other one. Which one? Do you believe to this dip or to this dip? They are both the same in terms of radiation. Okay? But of course, one is the earthquake. One is dipping on that side, the other one is dipping on that side. So geology is telling you, if possible, which one is the fault plane. And that's the other one. You see T and P, strike, dip, rake. And you see, for example, the numbers of the last digits are different. So all these estimations here have uncertainties. Here they are not reported. But for example, what is one uncertainty there? And it's a trivial one. To draw a beach ball, you assume a point source. Now you're saying that something that had been occurring on a 600 kilometers fault is a point. It's not. Okay? So here we are definitely adopting the point source model. That's why it's not accurate by definition. But now you can understand all of them and what is MW. So what I'm telling to you, look, 9.1. Which one is the best? Okay. So let's not trust to the last digit. Because also with the best methods available, we have uncertainties there. So I'm getting your point.
Is that oblique normal or oblique trust?
That's your homework.
No,
you can study too.
Yeah, I'm confused with white and dot black symbol inside the beach ball.
This one?
No, that one.
This one?
Yeah.
It's the same. It has the same. This is used to draw the axis. TPB.
So the central figure is the black one. Central circle is black one, or?
Are you referring to these two dots?
Yeah.
No, these are like T and P here.
Okay.
No, it's the same. Look, P is black because it's pushing, but it's attraction for the, okay? And it's inside the whites, remember?
Okay.
Let me answer to you. In a more polite way. It's just this vision. It's like this, okay? T, P. The convention there is to use black on white and vice versa, but that's it, okay? Okay, let's go back to our... Now we can read this. We know all the parameters there. For a point source, remember, a beach ball is for a point source. What I was trying to show to you now, we're going to conclude this lecture with some general messages that are important, because after the definition of a moment magnitude, now we know what is MW in principle. In practice, it's not that easy. But in principle, we have a beautiful definition of a theoretical magnitude. Now, there is something else that is related to magnitude, because of course, MW now is based on this. Can we draw some relationships between magnitude and on average area and dimension of the fault and slip on the fault? There is a seminal paper that I was adding here. Now it's an old one, but it was a new one at those times by Wells and Coppersmith. For the first time, they tried to use some relationships between slip, area, and magnitude. And this is important. You see that this scatter is huge, of course. But it's important because it's giving us some reference values. For example, let's take a magnitude, maybe 6, you can read it here, 7, you can read it here, and 8, you can read it here. So length, in a very simple fashion, maybe over simplistic fashion, but for example, for a magnitude 8, as you can see here, you go here, and it's hundreds of kilometers. 7, okay, you read it here, is tens of kilometers. 6, okay, 10 kilometers. It's a baby.
How did they estimate the?
Empirical value, so use a lot of error bars. You can do the dots are not all the earthquakes in the world, but these are the earthquakes for which you can measure error. Remember that in California, for example, most of the faults are on the surface. So you can go there and measure, and don't ask me how, but you can go there. In the Apennines, you can go there after an earthquake, and you can measure, you can estimate lengths. So magnitude is estimated by instruments, long period surface waves, okay? And you have this.
And what are the subtractions on this?
I don't know. That's why, that's why you have just a few points here. What you can do, for example, to measure them is to study the distribution of aftershocks. That's giving to you an image of a fault plane. You can call it as a very rapid post-seismic rebound. The aftershocks will be spread on the surface. And you can use that to estimate length and the area. Otherwise, there are many, you can use also paleoseismology. So you can dig a trench, and for example, you can measure slip. It's not a common procedure for all the earthquakes. That's why here you have just a few points. But it's just to give to you an idea of the dimensions. Of course, if you take 9, it's going with 1,000. Now, if you take the length here, 1,000, you see the average slip. So for a magnitude 9, slip is 20 meters. Wow. For a magnitude, let's say for 100, okay, it's 1 meter, and so on. And you see, a magnitude 6 that can cause a huge damage in vulnerable areas, actually the slip is not that much. On an area that is, okay, 10 kilometers. It's impressive, but it's, if you go back to this picture here, oh, it was the previous one. I also plotted the Italian ones, and it's quite ridiculous with the But you see the difference between this and this. What else? In the last set of slides, I'm just leaving to you some general messages, and one is, okay, it seems solve the problem now of energy, but please let's remember that energy is not only the kinetic energy, the part of the potential energy releasing kinetic energy of seismic energy. We have also friction on the fault. So part of the work is spent there. How much? That's a good question. That's a good question. And usually, these are very simple principles that are relating the stress drop that is available. Stress drop is more dynamic than moment, especially if you measure moment with seismic waves. And you see the stress drop here. That's the quantity that is giving to you the available energy. And of this part of the energy, maybe a tiny part is radiated by seismic waves. And maybe most of that is related to friction. Just to tell you that there is a parameter here, based on this very simple energetic consideration, that is giving to you, it's called seismic efficiency, the ratio between the energy released or in terms of seismic waves and the total one. And that portion, that number, sometimes is low, some percent. So please remember that from a dynamic point of view, stress drop is more important. And in what we did today, we assumed that stress drop for earthquakes was constant. That's another part to be. It's a good general assumption, but definitely we are not sure about that. But it is between 10 and 100 bars. Okay? So, message, please do remember, this is the estimate. Please do remember that efficiency is a way to measure how much part of the energy is released in seismic waves. As you can see here, sometimes it's a tiny number. For example, part of the energy of a Tohoku event was released for tsunami. We will see in the last lecture, we will try to make a very rough estimate to understand how much energy is in a tsunami. You would say it's huge. It's just a tiny fraction compared to the initial energy related to stress drop. Okay, I like this slide because there is another feature that is important. Maybe it's trivial, but it is important because every time that we consider a step of 1 unit in magnitude, remember that in principle magnitude is one number for one earthquake. We started with intensity, many numbers for one event, okay? Maybe from 11 to 1, or maybe none, if in a desert. But magnitude in principle is one number for one event, and it's not expressed in degrees. It's not an integer number, by definition. But 1 unit in magnitude, actually, if you give a look to the definition here, that's 90 centimeters, and if you give a look to the energy, it's related to 1.5. So logarithm, so please do remember that one step in magnitude is 32 times in energy. So it's a huge jump. What's next? Okay, some funny pictures that are in some way, I think I updated it with the Toku. Let me check. That's not mine, but okay, the Japan. Let's try to use this one. If you give a look to this part, it's impressive. You know why? Because, for example, if you take this one, this pie of a cake is huge, it's one event. And if you sum, for example, all the events between 7 and 8, you see this is, okay, let's say 1 century here, it's tiny or comparable to this one. So if you consider a mega earthquake, due to the logarithmic nature of magnitude, in terms of energy, we are taking a very large slice of the pie, okay? Remember the logarithmic nature of this. And this is another vision. and it's ranking the largest 10 earthquakes. So the Japan that was impressing the world, it was not the largest. Now, with all the uncertainties of the case, we think that the largest earthquake in terms of energy occurred in the human history is the Chile 1960 event. The estimate is 9.5, but there are uncertainties there. That event will become important for the last lectures that we will have during the next week, because on Monday we're going to speak, and we'll cut some of the slides that you have there. We're going to speak about inelasticity of the Earth and Q of the Earth, and also giving a sort of adopting the perspective of hazard. And we're going to speak just briefly about seismic hazard in the other lecture, and we will conclude, or vice versa, with tsunami physics and hazard. So the Japan event and the Chile 1960 event, Valdivia earthquake, are definitely the most important ones, especially the Chilean one. Why? Because no one was waiting that the day after that event could kill people in Japan. No one was waiting for that wave. At that time, some satellite, no mobile phones, nothing was there, and no one was thinking about tsunamis. So the day after, the Japanese were impressed by such a large wave after thousands of kilometers crossing the Pacific, arriving there, say, what's this? That's why that event started the research in tsunami physics and tsunami warning centers, and that's why the Pacific Warning Center was active since 1970. Okay? But of course it was not active in the Indian Ocean in 2004. Now it is.
Sorry, just you have a mistake in the table.
Sorry, it's a PDF, so I cannot edit it. I'm sorry. You know, in another version of this lecture, there is my apple pie, but I cannot change it. But thank you. Which one, for example?
The table, the first. Yes, it's China.
Oh! I never noticed it. China is suffering for other reasons now. It's not for this earthquake. Okay? Thank you. Wow, it's. Huh. Okay. I will put my apple pie. It was animated by. I was thinking that this one was better.
Quite close.
Oh, good Lord.
Is it 2010 China or Chile?
No, that's Chile.
Okay.
Chinese, in many parts of a huge China, there are some very, how to say, hazard zones, because they have a lot of earthquakes, especially in the Himalayan belt. But the magnitude until now was not larger than 8 point something. That's enough, okay? Also because the rapid growth of Chinese cities is increasing vulnerability. Better, it's increasing exposure. But we will see during the definition of hazard. Hazard is not related to, okay, we will speak about this during the next week. But that's Chile. It's a sort of a baby version of this one.
Yes.
That's Chile. Thank you very much. Let's see if I'm able to find. I was using for. Let's see. Because a few years ago, okay.
This is also
Okay, I was using bits in Italian. I did it for. That's in Italian, but don't look at that. I was looking for. No, I have the English. What is it? Oh, good Lord, I lost it. Okay, that's my apple pie, but it's in Italian. Okay, that's Italian for Chile. It's not China, at least. Okay, so I prefer to use that one. That's Italian. So that's one version, but I wanted to show to you what it is. because I put the Italian faults. Let me check. Let me check. It's this one. Is it? Because I played this comparison here with faults. No. Okay, yeah, this one. So it's in Italian, sorry, but it's related to the Italian earthquakes. I was trying to play the same game that Setstein was using. That's Chile, that's Sumatra, that's Japan. Okay, that's not the last Central Italy sequence, but this was the earthquake that occurred in Emilia. I tried to plot by hand, so please just use it as an indication, but you see it's like a dot compared to this. And these events here caused 1,000, 3,000 victims, 1,000 victims, 3 is here, it's my country. Aquila event, you see, they really appear like babies compared to these ones, okay? But, so hazard in principle is low, lower than this, but vulnerability was much larger. So that's the topic about hazard and risk that we're going to discuss on the next week. Let me conclude this lecture here with a couple of slides. One is a nice one, very iconic vision, because maybe we can ask, okay, now we know something about moment, energy, magnitude, but what about the numbers of earthquake with a given magnitude? Well, that's one kind of vision. It's very iconic for newspapers. And it's nice because here we have energy. Here we have what we define today, okay? Moment magnitude, now you know what it is. We know that it's in a sort related or wants to be related to energy. That's another unit that I don't like, but just to have an idea here. And this curve here is showing us the numbers. So increasing the magnitude, the numbers, the numerosity decreases. Now you can say, is there a simple way to estimate it? Yes. And again, we started from Charles Richter today. Let's end with Charles Richter, and we have this. It's one of the simplest and maybe most important laws that we can define. It's called Gutenberg-Richter because they published in 1954. As a short name, it's GR law. And it's very simple. When they defined it, they were using MS because MW was not started when they published the book. And what they had been using was the catalog available to them. And they used, and this is important, a global scale. So they took the catalog, the worldwide catalog, starting from magnitude 5, because magnitude less than 5 is, you cannot measure all of them, as you can imagine, because many parts of the world we don't have instruments. While a magnitude 5 usually is recorded by global networks. So it should be there. That's why usually it's starting from 5. So they used this collection at a global scale, and they studied the numbers. And they found a beautiful law like that. So the logarithm of a number was with a straight line decreasing, and so it's a straight line. Well, you could say, well, it's not exactly a line, because for small magnitudes, maybe we don't have all of them. But, okay, on average, we have a line, and on average, for the world, B is 1. So nice and so beautiful, so that you can measure here the number of earthquakes per year with that magnitude. You have two different versions, incremental values, so all the earthquakes with magnitude less than, or by increments, so cumulative or incremental, so you have different versions. Why this law here is important? Because it's simple. But it's important for two reasons. One is a theoretical one, if you want, because now what we can do, this is a different version for a different time here. You see how it's dropping for number of earthquakes. This is logarithm of a moment, okay? Because nowadays we can use moment, not only mass. Now, let's imagine to write this as power law, okay? It's like that. Now we know that magnitude is related to moment, so we can write it like that. We can write it like that. And if B is equal to 1, that's it. That's a power law, a non-integer power law. And every time that you have power laws, fractals are there. So many approaches to study the distribution in time and space of earthquakes is using fractals. That's one message. The second message is another one. We will see in the next WED lecture, we're going to speak a little bit about hazard. This is the most used tool in seismic hazard. It's a powerful tool, but it's a risky tool, because here you're reading the number of events per year with that magnitude. Now question, what happens here? Still we don't know, because at a global scale, we can have all of them. But when your area under examination is getting smaller and smaller, we don't know what's the end of that line. Could it jump with, could it be something like that? Let's see if I have a hidden slide here. Okay, I decided to remove it, but okay, let's keep a look and let's conclude with this. Because there were many models on how this beautiful GR law is ending. Is it ending like this? And then stop? Or it's behaving like that? So is this the largest event in that area and it has a different time? Because you see now it's getting different. Or it's ending like that? You do understand that these two versions are giving different hazard. Because maybe you want to consider this one. Still, we don't have an answer, especially at a small scale. But the message, that's why I was removing this one. But the message to take home, and it's the final one for today, is that on a global scale, we have a beautiful logarithmic, or if you want, we have a power law, GR law, very simple. And B is equal approximately to 1. So summary for today. It's the last slide. And please do remember a couple of things here. We discovered how magnitude was defined and how modern magnitude is defined nowadays. Instrumental connected to a specific instrument, Richter, ML. Then moving from 0.8 seconds to 1 second to 20 seconds. Also to reveal different features like tectonic or nuclear explosions, okay. Saturation, and the attempt to use theory to overcome the saturation. And yes, let's use M0. Let's take the logarithm, let's multiply by 2/3, Pascal model, 1.5, it was there. Let's connect it at magnitude 8 with MS, game over. The game is over, but it's not. Because remember that to measure M0, by routine, we are using the longest periods available, and these are surface waves. But if you don't go at sufficiently long periods, maybe you can get saturation for mega earthquakes, like Toku and Sumatra. So if you want to assess magnitude for those events in a better fashion, we have to use the longest periods available. 3 modes of the Earth, last lecture of wave physics, or near field, static displacement, but we need something there, or tsunamis. And that will be, we are going to touch tsunami physics in a very simple way on the last lecture. Let me me spend just 1 minute trying to Google Weissenstein, because until not architects, okay, most of the papers were available there. But it seems on the right, there's a website. Maybe in the presentation is better. On EMI local. EMI local had been visiting ICTP a couple of times, also quite recently. He was giving courses about tsunamis, because EMI local is one of the worldwide most experts in tsunami physics. But when he was a postgraduate student, he was working with Seismology on the 3 modes of the Earth. That's why they published together this. So I'm pretty much sure that on click here for PDF. So what? But that's the long version of the paper. Since I know that I'm lazy, I was giving to you a short end of the story. But EMI local. Let me publication. There's a publication list. Let's see if it's Oh gosh, it's pointing. Okay, that's it. It's not that bad, that nice, but this is your homework. Okay, let's check the pages. Oh, just one. That's the Nature version. They also produced a better 2 pages longer version. You see, that's not that nice. Okay, let's try to use our imagination. That's your homework. It will take half an hour less. Read here, please. Log of frequency. Okay? Read here its moment in dynacentimeter. If you read here, that is S00, S02. Now, this part here, that's millihertz. So we are here, a very long period. Millihertz, because modes of the Earth, 1,000 of seconds. So we are here, and you see that in that part, it's still increasing. And now, if you use routine observations, you're getting this number. But if you use the modes of the Earth, you're getting that number. And this means from 8.8 to 9.2. Okay? So your homework is to find a better version and maybe a little bit longer. There is a publication produced by them, like 3 pages long, so not that much, and a good quality one. And that's your homework to check this one. This is S02, and that's why they reassessed the magnitude of a Sumatra event using the modes of the Earth. Okay?